in this bottle, hopefully you can see that in the bottom here there's some liquid water. And on the sides of here there's also some liquid water, some condensation that's condensed here, and there's a top on the bottle. So imagine that water molecules are escaping from the surface here, and all of the time we've got evaporation at the surface. Some of those molecules are condensed on the sides of the bottle, but some of those molecules would just drop straight back down, and there's an equilibrium formed there between the water vapour inside the bottle and the water liquid here and on all of those surfaces. So if I was to leave that bottle here overnight, as long as the temperature of the room didn't change, the level of water in this bottle should stay completely the same, should stay fixed. But at all times, water molecules are evaporating, condensing, evaporating, condensing. It's a dynamic system, so that forwards process, the evaporation happens all of the time. The reverse process, the condensation, happens all of the time. But the level of water stays fixed because those two things are happening at the same time in this closed system. If instead I was to take the top off this bottle and leave it in the same room for a period of time, perhaps overnight, what one would expect would be that this level would drop a little bit. And that's because, of course, now the water evaporates, and instead of being forced to condense back in here, we've allowed things to enter or leave. So this is now no longer a closed system. So in order for an equilibrium process to be established, one of the features is that it needs to be in a closed system. So like this bottle with the lid on it, closed system, so the water level should stay constant. The second feature is that this is a dynamic system, so the forwards and reverse processes are happening all of the time. Now I mentioned that, and I mentioned this constant level, but I kind of skirted around why that level would stay constant. So let's explore this idea a little bit further. So I'll put that out to one side. And again, with my highly technical kitchen apparatus, let's start with this. So imagine this bowl with water in it represents the reactants in a particular reaction. And imagine this bowl, which is pretty much empty, represents the product in this particular reaction. I don't have any beakers at home, but I do have some nice glasses, so we'll use these to do this experiment. So first imagine, at the moment we're at absolutely time zero. There's a concentration of reactants and no products. Okay, so I just went and grabbed the board. At the very start here, if you imagine that we've got a graph that looks something like this. This is the time in whatever units, let's call it seconds, and let this be the concentration in whichever units. Might as well go for moles per decimetre cubed, because that's fairly normal. Okay, so at the very start we've got reactants here, and at the very start in this example no product. Now let's imagine that the reactants react to make products. So let's call this glass. Imagine that those reactants are reacting and forming products, just like so. So I could fill this glass almost to the brim, bit of a limitation with the size of the bowl, but never mind. But the forwards reaction went quite fast there. Let's have a look at the reverse reaction rate then. So if I take this glass here and see how many products I can get back, well, not so many, because the concentration of the products was lower at that point in time than the reactants was at the start. So if I just move that across there, some of the products will react backwards to make reactants. Just like in here, some of that water will evaporate, some will condense all of the time. As soon as we make the products, because this is reversible and a closed system, then those products will go back to reactants. So after a period of time, the reactant concentration has dropped a bit and the product concentration has risen a bit. But of course it doesn't stop there, because the reactants continue to react to form products, and the products continue to react to form reactants, and on it goes. And eventually we reach a situation where in this case the volume of water being transferred across from reactant side to product side is the same as the volume of water being transferred across from the products back to the reactants. So eventually the rate of that forwards reaction becomes equal to the rate of the reverse reaction. In doing so, the reactant concentration has dropped down, and then as soon as those rates become constant, it levels off. That should be horizontal, but never mind. The product concentration has increased and again levels off. So in this portion of the graph, if you were to just look at the reactant concentration or just look at the product concentration, it looks as if nothing is changing. But in actual fact, the concentrations stay constant, but all of the time that forwards and reverse process is happening. Forward, reverse, forward, reverse, forward, reverse. But at this part here, we've reached equilibrium because the rate of the forwards reaction is equal to the rate of the reverse reaction. And at that point, we would give it this symbol, which means a system at equilibrium.